Here's a summary of the circular model and how it's relevant to everything that we're talking about. First of all, a radian is where the arc length along the curve is equal to the radius. Now, more specifically, we've got a circle of radius r about the origin. We've got an angle here, okay, an angle from here out to here, such that the arc length swept out by that angle is delta s. And of course, again, the radius of the circle is r. When this arc length is equal to r, then you have a 1 radian angle. Now, did I do this right? I think my angle, I think I didn't quite get the radian angle quite correct. Can you see which is greater, the delta s or the r? I think one of them is clearly greater than the other the way I drew it, but I'm looking from a different perspective. Okay? Anyhow, if we have another angle, an angle from here around to here, measured counterclockwise from the positive x-axis. Okay, that angle's phi. We draw the line, the radius from the origin to the position on the circle at that angle, and we get a y and an x coordinate. The sine, cosine, tangent, cosecant, secant, and cotangent of phi are defined in terms of the x, y coordinates in r. Sine being y divided by r, the cosine being x divided by r, the tangent being y divided by x, and so forth. And the cosecant, secant, and cotangent are just upside down from these. If you happen to have a unit circle, which is a very common very commonly used for the definition, then r equals 1, and you simply have sine theta equals y, cosine theta equals x, tangent theta equals y over x. And I'm not going to read those to you. You can see them. You should make sure you can draw this picture and write these definitions and all this anytime you want them. That's very important. Okay, and you should have learned to do this in pre-calculus, and you should have certainly applied this entire model fairly extensively in calculus when you're finding the expressions for the derivatives of the sine and cosine, if you're proving those. And you should have in an engineering calculus course. Okay, anyhow, if 1 radian is the delta s along the curve, then theta in radians, and I should probably write that down, it's implicit, is going to be the fraction, delta s is a fraction of r. Okay, so for this small angle here, it looks like delta s is about 1/3 or 1/4 of r. So that means that the angle would be 1/3 or 1/4 of a radian. Again, you need to process that if you haven't already. Now, if delta s is equal to circumference, if we got the whole circumference, an angle that goes all the way around the circle, which you think of as a 360-degree angle or a 100-grad angle, then delta s is 2 pi r, which means that the angle in radians is 2 pi r over r, or 2 pi. Notice I didn't write the radians. Radian is the default measure of angle. Anything you do in calculus has to be done in radians. Otherwise, you have all kinds of a mess when you try to do derivatives or integrals of these functions. Okay, so the default measure of the angle is the radian. We see then the 2 pi radians is 360 degrees. 1 radian is 360 degrees over 2 pi, which is about 57 degrees. And you might want to express that as 180 degrees over pi. In any case, I think it's 57.3 degrees. I didn't write that down because I haven't calculated it. Just remember it. Okay, now let's look at a small angle. If theta is small, then you have this picture. Okay, well, there's nothing surprising about that picture. This vertical line, purple vertical line I've inserted here, is a line whose length is equal to your y coordinate. So I enlarge this circle a little bit, and I draw the same triangle, and it's a right triangle. I should probably indicate that right angle. The rise of the triangle, or the side opposite the angle theta, if you prefer, is y. The coordinate that's used in defining the sine, the cosine, and so forth is y. Delta s is the distance along this arc. Okay? Well, the distance along this arc doesn't differ much from y. It would if you took the arc all the way around to here. Clearly, this arc from 0 to 2 pi radians is longer than the y coordinate, which is 1. But that's not the case when the angle is small. Okay? So, we say that y is approximately equal to delta s for small theta. And let's draw that small theta reference down here as well. Okay, y is approximately equal to delta s, and this approaches equality as theta approaches 0. And it's clear that this arc becomes almost vertical. And the closer you get to 0, the closer that arc is to vertical, the closer it matches your y coordinate. So that y is approximately equal to delta s. From that, we conclude that sine theta, which is y over r, is delta s over r. But we don't conclude that. Well, yeah, we do. Sine theta is equal to y over r, and that's approximately equal to delta s over r, since delta s is approximately equal to y, with an approximation, again, that gets better and better as you approach 0. It approaches perfection as you approach 0. Theta is then delta s over r, so that and of course, theta is delta s over r because you're simply dividing the arc distance by the radius according to our definition up here. And tangent of theta is approximately equal to sine theta then. Okay? Since tangent of theta is y over x. For small angle, we showed in a preceding video, in the video that immediately preceded this one, excuse me, starting to think I can talk. Okay, we showed that x is approximately equal to r, and then it follows that tangent of theta is approximately equal to sine theta for small theta. So you have all these approximations. Theta being delta s over r is approximately equal to y over r, and tangent theta is approximately equal to sine theta. Again, you need to understand these deeply. You should be able to reproduce this whole argument in 5 minutes anytime you need it.